This is going to take a little while, so strap yourself in, get comfy. Here we go. Oxidation. Don't forget oxidation, of course, is a process by which a reducing agent loses one or more electrons. So oxidation is losing electrons. An oxidation half reaction, electrons are shown as the product, so don't forget that. And an Ra is oxidized, experience an increase in oxidation number. Okay. Reduction. Obviously gaining electrons, one or more. It is the electrons are shown on the reactant side. The OA is reduced. It experiences a decrease in oxidation number. All right. All important things that you need to know about those. If we want to build a table of half reactions, remember we have to write them as reduction half reactions. They're always written as that. Spontaneous versus non-spontaneous for right now, and that's what we're going to be doing with this one here. Okay, so let me move this down here. Here we go. So remember, spontaneous versus non-spontaneous. S2 plus is gaining electrons to become S solid. So S2 plus and 2 electrons gives me S solid. That has to be higher. S2 plus has to be higher than T because it is a spontaneous reaction. Something's happening there. So T solid would have to be down here somewhere. And of course, the charge that goes with T is what? 2 plus, I believe? Yeah, or 1 plus. So T 1 plus and 1 electron gives me T solid. Okay, so I know that that's true because, of course, S2 plus is up there, T solid's down there. All right, so that's the first thing. Next, it says R3 plus, this and this. There's no reaction, so that must be a non-spontaneous reaction. R3 plus must be lower than T solid, so R3 plus would probably go down here somewhere, like so. Okay. And just to save a little bit of time, I'll skip the states there. And then finally, it says R3 plus and V solid, there is a reaction. So I know R3 plus has to be higher than V solid, and V, of course, has a 2 plus charge. Okay, like so. Okay, so that would be my table of half reactions. Okay. Thank you. Good? Yes? Okay. That's easy, right? No problem. So, spontaneous, non-spontaneous. By the way, I guess I should mention here, sorry. If the OA is higher than the RA, right, that is spontaneous, yes? Otherwise, reverse, non-spontaneous. Okay? Next. Balancing redox reactions. Most likely reaction to take place with iron. I think there was some cobalt there, some aluminum, some nickel, some hydrochloric acid. So remember, in this unit here, we didn't really write out H3O plus, because if you look in the data booklet, there's actually no H3O plus. It's back to H plus again, right? But H plus, Cl minus, and of course, yes, water. Don't forget, there's some solution there. Okay. What's the most likely reaction? Well, you're going to get your data booklets out. You're going to start in the top left, of course, and you're going to start working your way down until you find something. One of these, what is there? 6 things, 7 things here. You're going to start in the top left and start working your way down, and you'll find that this right here, H plus, is your strongest oxidizing agent. That's the most likely to gain electrons. Yes, oxidizing agents gain electrons because they're being reduced. Yes, that's the most likely one to get reduced. Therefore, it's the most likely oxidizing agent in this case. You start in the bottom right and start working your way up. What's the most likely one here to lose electrons? And that would, of course, be aluminum here. That would be your SRA. In other words, that's the most likely one to lose electrons, be oxidized, or in this case, be your SRA, reducing agent, strongest. So it's basically those 2 things there. You're going to write out a table, the 2 half reactions from your data booklet. So reduction half reaction looks like this here. I believe it's 2H plus, and 2 electrons gives me H2 gas. Okay, and the oxidation half reaction, the most likely one to lose electrons, of course, is aluminum solid. and that would give you aluminum 3 plus and 3 electrons. We will write out the net redox reaction. So the redox reaction, of course. And to do that, we need to make sure that we balance these. So I'm going to take this one here times 2 times 3 to balance out the electrons. Okay? And therefore we will get, as a final answer, 6 H pluses and what is it? 2 aluminum solids and 3 H2 gases and 2 aluminum 3 pluses. And once again, all said and done, remember in this unit we want to check, make sure our balanced everything and we have everything balanced appropriately, etc., and check charges. For example, on the left side we got 6 plus, on the right side we got 6 plus, probably okay. 2 alumins, 2 alumins, 6 hydrogens, 6 hydrogens, that's good. Okay, so that's that one there. Balancing redox reactions under acidic conditions. All right, so under acidic conditions, once again, you see 2 parts here. This isn't going to show up very well, but that and that, right? So we have to decide here. Remember, if it's under acidic conditions, the way we do that is, well, first of all, there's numerous ways you can balance these types of equations. You can do data booklet stuff like we just did, okay? I don't think you're going to find that in the data booklet. I doubt it. You can look, but it's not going to be there. You could do oxidation numbers, which we'll do later. And finally, you can do acidic conditions or basic conditions. This one says acidic, so we have to start somewhere. Which one is actually being reduced here? Which one is being oxidized? To be honest with you, if you looked at this, maybe you don't have a clue. That's okay. You got to start somewhere. So I'm going to start with this one here. I don't think I can move this down here, but I'm going to start with Cr2O5 2 minus, aqueous. And of course, that turns out to be on this side here, a chromium 2 plus. Right? How do I know to match it up? Look, chromium matches up with chromium on that side, right? So that's where I got to start. Then I say, okay, how am I going to balance the rest of this? Well, let's see. First of all, I'd probably say, look, I got 2 chromiums here. I need 2 chromiums here. Yes? Okay? So 2 chromiums there, 2 chromiums there. I have 5 O's here. I have no O's over there, so I guess I should probably add some waters. 5 O's. Okay? But because I've done that, now I've added 10 hydrogens to that side. Now I'm going to add 10 hydrogens to this side. There's my acidic conditions. All right? And once again, we're not quite done yet because the charges don't balance out. You'll notice on the left-hand side we got 10 plus and 2 minus, that's 8 plus. On that side we have a 4 plus, so I'm going to add 4 to this side here. Well, now that I've done that, I know now, in fact, that this is my reduction half reaction. So therefore, I'll put my reduction half reaction. By default, that makes the other one an oxidation half reaction. Okay? And the oxidation half reaction has to start out with this C3H7OH liquid, I guess it is, or something, or aqueous, I guess, aqueous. And that has to, of course, go to CO2 gas here. Same thing. Start by balancing. You know, don't be adding waters and stuff like that until you balance basically the major elements here. Don't worry about hydrogens and oxygens, but there is 3 carbons here. Let me start by putting a 3 there at least. Okay? So, on the right-hand side, I got 6 O's. On the left-hand side, I got 1 O. Let me add 5 O's. And of course, to add 5 O's, I'm going to add 5 waters. Well, now I've got 10 H's and another 8 H's here. So there's 8 there and 10. That's 18 H's. So I need to add 18 H's over here. Okay? Well, now I have to balance out the charges as per usual, right? Everything else is balanced. So now I got 0, 0, 0, 18 plus, 18 minus, 18 electrons. Once again, that does work out to be my oxidation reaction. I must have done it okay so far. At least I'm on the right track because one's a reduction, one has to be oxidation. If you're going to gain electrons, you got to gain them from somewhere. Make sure you gain them from, of course, probably the oxidizing equation here, right? Redox. Here we go. I need to balance out the electrons. I got 4 and I got 18. The lowest common multiple of 4 and 18 is 36. So times 9 times 2. Okay. Now, I'm just going to start with the major stuff. I'm not going to worry about the hydrogens and waters right now. I'm just going to start with kind of the major stuff here that I need to obviously have here. So 9 Cr2O5 2 minus aqueous, and I'm going to have 2 C3H7 OH aqueous. On this side here, I'm going to have my 18 chromiums, 2 pluses, and my 6 carbon dioxides, gases. Okay, that's kind of the major stuff, right? That's the important part. And then of course I got the water and I got the acids. So don't forget, technically right here I got 90 H's. Here I got 36 H's. So 90 and 36 is a net of 54. Yes? 54 H pluses. Okay. Same thing with the water. Up here, I got 45 waters, and down here, I have 10 waters. So that should be a net of 35 waters over here. Okay. And, you know, first things first, I would probably check to make sure the charges match up. That's the first thing I do. And if that does, yeah, you're probably okay. Not guaranteeing it, but you're probably, at least you're, you know, got that part balanced. If the charges don't balance up, I'll tell you right now, it's not good. Okay, it's bad. But 18 minus and 54 positive is 36 positive and 36 positive. So that should be good. Okay. So once again, I know it's right because I did it before here. So, but you know, if you really want to spend the extra time, if you have time, go back and balance each atom again, and should be okay. All right. So that's under acidic conditions there. Okay. Oh, good old review. Don't you love review? Oxidation numbers. Cyclobutane, 2-chloropropane, pentanoic acid, butylpropanoate. All good questions. Cyclobutane, burp, 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 that is C4H8. Okay, cyclobutane. Cyclobutane, of course, hydrogens are a 1 plus oxidation number. So 1 plus, which makes that a 2 minus, right? Neutral molecule, so the overall charge on that has to be 0. So if that's 8 positives, that has to be 8 minuses. Next, 2-chloropropane, propane, 2-chloro, H3, H, H3. So that gives me C3H7Cl as a formula. Hydrogens are 1 plus. That's easy enough. We know that. Chlorine is a electronegative atom. So if you're not sure between carbon and chlorine, chlorine's the more electronegative atom. Therefore, chlorine has to be assigned its oxidation number first, which of course is usually, and you wouldn't be wrong, 1 minus, yeah? Chlorines are usually 1 minus. So you're going to assign that one first. So that's 8 positive. That's 7 positive, 6 positive. So each one of these has to be a 2 minus, okay, to get back to what you need there. All right, balancing those out. Next is what? Pentanoic acid. Perfect. Pentanoic acid looks like that. Yes. Filled in with some H's here. H2, 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 H3. Okay. That would be C5, H10O2. Once again, hydrogens are a 1 plus, oxygens are a 2 minus. So 1 plus, 2 minus. That is a total of, let's see, 10 positive and 4 minus. So that's a 6 positive, which means I need carbon to be a 6 negative altogether. So therefore, each one of these is a negative 6/5. Okay? Negative 6/5 times 5 is a negative 6. All right? And finally, butylpropanoate. Butylpropanoate. So That means that that double bond O is in the middle. Okay, that's propanoate. Propanoate came from what, by the way? How would I make that propanoate part? Comes from what? Propanoic acid. The butyl came from what? 4 carbons. Butyl came from butane 1-ol probably, yeah? Yep. Alcohol. Okay. This is called a what? Ester. This reaction, if I mix the carboxylic acid and the alcohol, is called a esterification. You bet. So, fill in the rest here. H3, H2, that's good. H2, 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 H3, and the formula for that one here works out to be C7H14O2. Same thing, 1 pluses, 2 minuses, so that's 14 positive, the 4 minus, so that's 10 positive, so this has to be a negative 10, so it's a negative 10 sevenths, because negative 10 sevenths times 7, of course, is a negative 10. Okay? Good? All right. Next one. We're going to switch this one on yours, guys. And it's not that we can't do this one, but ultimately this one's a little bit more complex. So you have to use a fraction for this one. And not that we can't do it, but we don't need to worry about that, I don't think. Okay? So I'm just going to rewrite this. All you guys have to do is cross out the first one and write this down. Okay? Everything else is exactly the same. So just cross out the first one, and you're going to write there instead C5H11OH. And you got your chromate here. So this is the same as before for you guys. Okay? And your H pluses here. And that's going to give you CO2 and H2O and chromium 3 plus. Okay, oxidation numbers. You want to balance based on oxidation numbers, I guess. So 1 plus, 2 minus, 1 plus. I'm just going to do the easy ones first. 2 minus, 1 plus, 2 minus, 2 minus, 1 plus, 3 plus. Okay, so let's see. 11 positive, 12 positive. So 11 positive, 12 positive. 2 minus, that's a 10 positive. I need 10 negative here, so that's a 2 minus. Okay. This is 8 minus here, and then I need a 6 positive right there to get the 2 minus charge. Don't forget the 2 minus. If it's got an ion, it's got a charge. Don't forget you're going to need that. Yep. Yep. 1 plus. This is a 4 minus. This is a 4 plus. And I think that should be good. Okay, I probably should have done that all at the same time, but I didn't want to, so too bad. Chromium is going from a 6 plus to a 3 plus, so that gains 3 electrons per chromium, don't forget. And I know that's a little thing there, and you might not want to do that, but remember, based on each atom, okay? Therefore, in total here, yes, gains 3 electrons. Obviously, if it's gaining electrons, it's being reduced. If it's being reduced, it's your oxidizing agent. I'll put OA up there. Okay? C is going from a 2 minus to a 4 plus. So, once again, that's being oxidized. It's going up in charge. If it's going up in charge, it's being oxidized, so therefore that's your reducing agent. This means it's loses 2 minus to a 4 plus. So you got to remember that. 2 minus to 4 plus, that's a difference of 6. Yes? 6 electrons per carbon. In total here, we're losing, per carbon, there's 5 carbons, so loses 30 electrons altogether. Okay? Then you're going to do this little thing here. I need to balance out the electrons, right? If I'm gaining 3 there, but I'm losing 30 there, that doesn't match up. That ain't cool. All right? So times 10 times 1. You're going to put a 1 here and a 10 there. Okay? That's absolutely guaranteed, right? Once you've done that, you can't change those numbers, right? That's what you've balanced it on, because that's based on the electrons that you've lost and gained. Now, You got 5 carbons here. So right here, I'm going to put, oops. I'm going to put 5 carbons there. That's done. Okay, I can't change it. 10 chromiums means I got to go to here and put 10 chromiums. All right. H plus leave till the end. Water's the next thing you should be balancing because oxygens are going to be a little more tricky, of course. Over on this side here for oxygens, I got 1 here. So 1 right there, and I got 40 there. So that's a total of 41 O's on that side. On this side here, I have 10, and that's it. So I have 10 O's on that side. I need another 31, yes? So I'm going to put 31 here. That makes it 64 hydrogens on that side there. So now I have 64 H's there. Here I have 12. All right. So 12. I need another 52 right here. All right. Where? 62? Oh, oh yeah, 62, sorry. 62, yeah. Okay, 62, and so therefore I need what? That's not right then. Give me a second here. That's 12. I need 50, yeah? Is that better? Thank you. 50 H plus is there. Okay? And once again, if I would have left it like that, you would have saw that they don't balance out, right? So checking right now, real quick here, what is this? 50 positive, 10 2 minuses. So that's 20 minus 50 positive, that's 30 plus, and that's 30 plus there, so that works out. Okay? So it should be good now. All right, thank you. Good? Okay, moving on. Disproportionation reactions. All right, well, once again, how do you know you got disproportionation? Well, one of 2 ways. 1, they'll tell you. 2, well, look, you only have 1 reactant. So I guess this reactant looks like it's probably doing 2 different things. Probably losing electrons, probably gaining electrons. So what I'm going to do here is I'm just going to probably rewrite this out here and then go from there. So let's say here H2 PO2 minus, and that gives me, oh, by the way, you guys are going to add something on for me here. You're going to add on an H plus at the end. Now you don't have to, but when it all comes set, when it all is finished and stuff like that, it won't balance out. That's okay. You would just add in some H plus because probably under acidic conditions. So it's not a big deal. You could add some waters, etc., etc. It's fine, okay? But you probably will need that H plus there. So put that on at the end of yours there as well, okay? It'll just make it balance easier. That's all. All right. Let's see here. Let's oxidation numbers, I guess. See? So this is a 2 minus. This is a 1 plus. So that's 4 minus, and that's a 2 positive, so that's 2 minus. This would have to be a, what did I say? 4 minus, 2 positive, 2 minus. That has to be a, no, 1 positive, right? 1 positive, I believe. 4 minus. 2 minus, yeah, okay. 1 positive, that makes that a 3 minus. That's a 2 minus, that's 8 minus, and that has to be a 5 positive, and of course that's a 1 positive there. Okay? So, you can see that the phosphorus is going from a 1 plus to a 3 minus, and the phosphorus is going from a 1 plus to a 2 minus. So, don't forget, you'd probably want to use double arrows with this here kind of thing. So, you got to keep these straight. If I'm going to do this one here, to that, okay? That one, okay, we've talked about basically there. Well, actually, you know what? Before I even start that, before I even do that, maybe it'd be better if I just wrote this out twice. That's what I did last class too. I'm trying to take a shortcut here. Let's just do this. So we know that this one and this one here have kind of different roles, right? This one here may be gaining or losing. The other one may be gaining or losing depending on which one we're going to do here. So pH3, PO4, 3 minus, and an H plus. Okay. Now, let's do this one here. I'll go from there to there. Now, we said in that case there, you can look above there for kind of reference, guys. P is going from a 1 plus here. These are the same thing, right? So 1 plus to a 3 minus. So 1 plus to a 3 minus, that is being reduced. Yes? Yes. 1 plus to 3 minus, reduced. Therefore, it's my oxidizing agent. It is gains 4 electrons per phosphorus, or gains 4 electrons, yes? 1 plus to a 3 minus. That's gaining 4 electrons, yes? This one is going to go to this one here. I've decided. I just picked them. You didn't have to pick those ones. You could have done whatever you want. Outside ones, inside ones, doesn't matter. This is a 1 plus. This is a 5 plus. So it's going from a 1 plus to a 5 plus. It's losing 4 electrons. Okay? Loses 4 electrons per phosphorus, or loses 4 electrons. This, of course, is my reducing agent in this case. Okay? Well, gains 4, loses 4, perfect. Times 1 times 1, yeah? Now, it's not always going to work out that way. It is very, very, very important with disproportionation reactions that you track where you're putting those electrons. Because when I put the 1 here, okay, now it didn't work out so well with this one because this is just a 1-to-1 ratio. So it doesn't make as much sense. But if you go back and look at your notes, or if you go back and look at the YouTube thing, you'll see when I put a 1 here, that means that if I'm putting a 1 here, I'm following this over and I'm putting a 1 there. Those two go together. Yes? That's why I put the arrows there. Okay? It doesn't matter in this one because, yeah, this one's a 1 here and it goes to that one there. Yes? I get that. But, okay, those two have to balance out. Those two have to match up. Once again, P here, P there, P there, P there. You got to balance based on inspection. Don't worry about the oxygens or hydrogens. You can't worry about those till the end. Okay? Then you'll see here, okay, well, I got 4 H's here, right? I got 3 H's here, so I need another H there. That's my 4 H's on that side there. Check out the O's. You got 4 O's there, you got 4 O's there. That's all good. Okay? That's why I put that H plus on there, just because it makes it a little bit easier to balance, other than just assuming it's under acidic conditions, of course, which it is, probably is. Okay. Then, once that's all done, we need to basically combine some stuff back together here. So you'd probably go back and say 2 H2PO2 minuses gives me 1 PH3, PO4, and 1 H plus. Okay? Kind of like that there. You don't have to put the 1s there, of course, but that's your basic balanced final equation. Yeah? Yep. Like I said, it's probably under acidic conditions. I didn't put that in there, but remember, you could probably add some water if you had to. You couldn't add water in this case because it's already balanced with the oxygens, but you do need an H plus there somewhere, so you probably just have to assume that it's under acidic conditions. That's all. Yeah, probably write 2 of them, because one is going to be losing electrons, one's going to be gaining, right? Yeah. Stoichiometry. All right. Once again, you can balance this however you wish, guys. You really have 3 options: data booklet, oxidation numbers, or you could do under acidic or basic conditions. Now, this one doesn't say, so it might be a little tough, but it doesn't really matter ultimately, because really, this is the important part here, right? Look, guys, I'm trying to link this to this, yes? So really, that's all I care about, correct? Ultimately, I need to get the ratio between those two. So whether you do it under acidic conditions or basic conditions or whatever, it doesn't matter. However, I'm going to do, I like to do oxidation numbers because it's probably easier and quicker, I think. So Cl2O minus, Sn, and over here I got Cl2 and SN2 plus. Okay? So that's what you're starting with. Oxidation numbers, of course. Let's see. 2 minus, That's a 4 minus, so Cl has to be a 3 plus. That's a 0 for elements, 0 for elements, and of course that's a 2 plus there. So it looks like Cl is going from a 3 plus to a 0. So this is your, that's being reduced. So this is your OA. It gains 3 electrons per chlorine, gains 3. Okay. Tin going from a 0 to a 2 plus. It's being oxidized. So it's a reducing agent. Loses 2 electrons per tin. Loses 2 electrons. All right. We've got to balance those out. So can do times 2 times 3. Remember, 3, 2, those are set. Can't change them. 2 chlorines, I got 2 chlorines already. So look, 2 chlorines, 2 chlorines. I'm going to put a 1 there because I know that part's been balanced. So I know that that's been done. Leave it. Okay. 3 tins, 3 tins. Now, is it actually balanced? And the answer is no. Okay. You're short a little bit here, right? Look, everything looks good except for the oxygens, of course. So, you know, ultimately, do I need to worry about that? Not in this question, no, but I'll finish it off for you. Look, 4 O's there. I'd probably want to add 4 O's there, which means I've added 8 H's, so I'd probably add 8 H pluses there. Okay? Does that work out? Does it balance now? Absolutely. 2 minus 8 plus, that's 6 plus, and 6 plus, good. Perfect. Do I need to do the last little part there? The answer is no, not for this question. To save some time, I wouldn't have done that because I honestly don't care about this. And I don't really care about this either because remember, I told you I'm focused on this compared to this. That's the stoichiometry I'm doing. So once I have those 2 numbers, I'm done. I don't even care about, for that matter, I don't even care about the 3 SN2 pluses there at the end. The stoichiometry part with that was, let's see here, calculate the mass of chlorine. So I'd put that there underneath the chlorine, of course. When you had 15 grams of, what is it, tin, yes? So molar mass is 118.71 grams per mole. N is 0.126 moles. I'm going to move that over to there. Divide by 3, of course. That's what I really cared about right there. That's why I had to balance it. And N here works out to be 0.442. Molar mass is 70.90 grams per mole. And the mass here works out to be 2.99 grams. Final, all said and done. And once again, line it up underneath there, right? Keep it nice and neat so you know. Okay? And that would be that one there. Good so far? Yes? So a little bit of stoichiometry using oxidation numbers. Next. Oh yeah, Voltaic cells. Awesome. Now, I am going to change this one a little bit here because we are kind of missing a little bit here again. I don't know why these are different a little bit. I'm not sure about what happened, but it should say iron acidified permanganate Voltaic cell. But just put in the word acidified because it matches up a little bit better with your data booklet. I'm not sure if that's necessarily, yeah, I don't know what's going on there. But anyway, just put in the word acidified. That'll make it easier for you. So, Voltaic cell, okay, it says sketch and label a diagram of this. When we talk about Voltaic cells, we have to think about, right, still that data booklet, still the table. We have to think about what's all the stuff that I have here, what is possibly gaining electrons, what's possibly losing electrons. But remember, we don't write down reduction oxidation anymore for this, although that's really what it is, reduction oxidation. We call it cathode and anode, right? That's what we call it now. Cathode is reduction. Reduction always happens at the cathode. Anode oxidation always happens there. So that's what we need to write down instead. That's the only difference. Other than that, it's the same stuff as before. So here we go. You know what? I'm actually going to write this out in this class here. At the cathode, actually, sorry. No, back up here. I'm getting a little excited here. Voltaic cells. It's an iron acidified permanganate. So I got some iron. I have some acidified permanganate. Probably got some water as well. Okay, voltaic cell. So that's basically what I have. Remember, it's got to be made up of 2 half cells. So if I got iron, what else do I possibly have in this? Iron what? Iron what? 2 plus, yeah? If you look up your data booklet, iron goes with iron 2 plus, right? I mean, it says iron, so it probably legit, it's probably iron. But iron does form an iron 2 plus ion, okay? So, looking up in your data booklet there on the table. I don't know if I'd write that down necessarily, but you got to think about half cells, right? If I got iron, what's the ion that's probably going to go with it? And the answer is iron 2 plus probably, okay? So, you're going to look through all this stuff here. You're going to find basically the SOA and the SRA, yes. You'll find that this part right here is your SOA, and that's your SRA. When I say that, I mean you're going to start in the top left and you're going to start working your way down until you run into one of those things. The first thing you run into is the H plus and the MnO4. That's the one most likely to gain electrons, the SOA on the top left. Then you start in the bottom right and you work your way up, and iron is the most likely one to lose electrons. So it's the SRA. Okay, so I'll write this out maybe. The actual equation here, just so you, for a little bit of review here, is actually, I don't even have it, to be honest with you. What is it? 8 H pluses, I think. Where am I here? Oh yeah, MnO4. No. MnO4 minus and 8 H pluses and what is it? 5 electrons gives me Mn2 plus and 4 waters. Okay, so that's what would be happening at the cathode. At the anode, I would probably be starting with some iron solid and getting iron 2 plus and 2 electrons, like so. Iron solid, iron 2 plus and electrons. Yeah? Yes? Yes? No? Yep? Sure. What do you mean? You good? Okay. That's all I'm going to do. Yeah. That's what's happening at the cathode. That's what's happening at the anode. If you want to write the net cell reaction, yes, you'd have to balance it like we did before, yes. You know, times 2, times 5, balance it all out. I'm not going to do that, okay? I don't think we have to do that, do we? No. Yeah, kind of the next question, although the next one is the cell potential and cell notation, a little different. So we'll talk about that in a second. So you didn't really have to do this, but I just wanted to show you. Remember, that's at the cathode, that's at the anode, so that's what's happening. So when I go to draw my diagram, remember, it's up to you. You don't have to do it this way. I like to put my anode there. Beaker, water, solution, salt bridgey. I'll put in here. Anions go towards the anode. Cat ions go towards the cathode. Yes. Okay. So anions go towards the anode. Cations go towards the cathode. Electrons always go towards the cathode, of course. Yes. Sometimes you may see here a voltmeter kind of thing, just basically to register it, or a light bulb or something or whatever, I don't know. But basically that you know it's just a voltmeter. If it says power, that's different. Power PS or power supply, we'll talk about that one coming up here. But this is just a voltmeter. It just measures how many volts are traveling through there, which we could find out by doing what we do next here. Okay, at the anode, we have iron, solid chunk of iron. And it's losing electrons to make iron 2 plus aqueous down here. Don't forget to show me the arrows, which way they're going, right? So that's making the iron 2 plus aqueous. Those electrons are traveling up and through and over to the cathode here. Do I have a solid chunk at my cathode? Carbon or graphite or platinum, yes? Because in this particular example, I do not have a solid metal. So I need carbon, I need the inert electrode, yes? Then down here, what you're going to put in is the following. H plus, and I don't need the specific numbers, guys, and MnO4 minus are combining, right? They come together, both of those are gaining the electrons, those two together are gaining electrons, and I'm getting water and Mn2 plus. Okay, and I know that because that's what it says up in my cathode equation there, yes? So that's what's happening. All right? So H plus and MnO4 are turning into H2O and Mn2 plus. Good? Yes? That'd be a diagram. Like I said, I kind of messed this part up here. Maybe I'll just get rid of that and do volts. It would be going that way. Electrons, of course, traveling towards the cathode, etc., etc. Yeah? If you're going to do cell notation, which is the next part here, cell notation, remember, always is in a specific order, always has to be in this order. It goes anode, anode electrolyte, salt bridge or boundary, cathode electrolyte, cathode, right? Think of it alphabetically, I guess, in a way. So the solid chunks have to be on the outside part. So it goes anode, anode electrolyte, cathode, right? A to C kind of thing. And like I said, the solid chunks have to be on the outside. So right here I put in iron solid. My anode electrolyte was the iron 2 plus. My salt bridge or my porous boundary or whatever the case might be there. Carbon electrolyte, or sorry, cathode electrolyte has to be everything that you see in the electrolyte solution, in that solution. So it is H plus, MnO4 minus, it is H2O, it is Mn2 plus, and finally a carbon or graphite or platinum inert electrode. Okay, so that's what you'd have there. Okay, don't forget it's everything that you have in that electrolyte solution there. So in that case, it's all that part. Yep. Yeah, we just put it in there because that's what it forms from the cathode half reaction. So I know it's already in there, but that's part of it. Yeah. All right. Good. Okay. Okay, that's that. Oh, no, it's not good. Net cell potential, yes, is the next thing I think it says on that question. So net is the cathode minus the anode. If I want to find the net cell potential of this here, I'd look up the iron, of course, and the H plus MnO4. The H plus MnO4 one is a 1.51 volts, the cathode in this case. And we're going to subtract from that a negative 0.45 volts from the anode, the iron one. And that gives me a total of 1.96 volts. That's probably what you would see on the top part there. If you had a voltmeter there, you'd see 1.96 really measured. Okay, so that's the net cell potential for that, for those two half reactions. All right. That's if that was all running together, right? So what I'm saying is, you know, once again, altogether, the net cell potential is 1.96, okay? What we're going to do now is we're going to say, okay, if the whole thing is 1.96, and I know how much the anode is, I could figure out how much the cathode half cell reaction would be, or vice versa, right? And that's what we're going to do, I think, next. Maybe not. Yeah, we are, okay? On the next page here. So using that formula, we're going to sort. I should have done that there, I guess, but whatever, same thing. We're going to sort these out now according to basically net cell potential, right? Or half cells, reaction to half cells. So just like in your data booklet, those you know, SOA to SRA are organized according to half cells. Those are all half cell voltages, right? Based on that. So we're going to do the same thing here, but remember, in your data booklet, we use hydrogen as the half cell reference. It's the one that's got 0.00 volts in your data booklet. I don't want to use that one 0.00 volts as your half cell reference. I want to use, in this case, dysprosium. Okay, so I'm going to use that instead as the half cell net reference, or reference half cell, I should say. So right away, I know that if I'm going to use that as the half cell reference, that has to be 0. Okay, so dysprosium here has a charge of 3+. I'm going to put it, I don't know, here somewhere. 3+ and 3 electrons gives me dysprosium solid, and that's where I'm going to put my 0.00 volts. Okay, because it is the the reference half cell. All right. You have to write these always when you're doing these tables. They have to be reduction half reactions. They always are. They always will be. Okay. Next, if I know, look, if this is 0 here, I know that also dysprosium in this particular equation here is my anode. I know that because my cathode is the one that gains electrons. Look, Tb3+ gains 3 to get back to 0, yes? So this has to be my cathode here. So if my cathode minus 0 is 0.92, well, I guess my cathode has to be 0.92, yes? Okay, so I'm going to save a little bit of work on that one. Tb3+, and if you don't understand what I'm doing here, we'll do it for the next ones here, but I just want to save a little bit of time here. That's 0.92 volts. Look, if that's my cathode, and this one is acting as the anode, this is 0.92 minus 0, cathode minus anode, gives me the net of those two, which is 0.92, C minus A. Okay? Now, the next one here. Now I got those two done. Okay, look. Oh, here's Tb3+ again. It's my cathode. This is my anode. The cathode minus the anode has to be 1.41 apparently for the next equation here. So down here somewhere I'd say the cathode minus the anode has to be 1.41. The cathode in this case is my Tb3+ one. I know that has a half cell voltage of 0.92. So what's my anode going to work out to be in this case here? Well, solving for A, all said and done here, yes. So when I solve for A, I should get what? It's about 0.49, and then negative A, of course, is 0.49, so A has to be a negative 0.49 volts. Okay? So when I go back up to the top here, looking at A in that case was the FM half cell. Okay, the FM half cell has a voltage of negative 0.49. So I'm going to write out the half cell for that. FM, is it a 3+? Yeah, 3+, and 3 electrons gives me FM solid, and that would be a negative 0.49 volts. Okay. Last one is the YB3+ and FM. So once again, the YB3+ right here, that's acting as my cathode, that's my anode. When I subtract those two, I should get 2.03. All right. Well, I know FM, I just figured that one out. So C minus A down here, C minus A has to be what, 2.03? A, I already know, was my my negative 0.49 here, 2.03. C must work out to be, that's a positive 0.49, so when I subtract that from both sides, I will get 1.54 volts. Okay? 1.54. So that'll be my YB one, half cell, 1.54. So YB 3+ and 3 electrons gives me YB solid and 1.54 volts. And we've organized them in basically strongest to weakest net cell, or sorry, half cell reduction, half cell potentials. Okay? Remember, after you've done all that, basically what they're telling you is that this is, once again, we can refer to that as the SOA. And of course, this would be my strongest reducing agent. Remember, just like the acids we did, the strongest ones in the top left, the strongest base is in the bottom right, or in this case, the strongest oxidizing agent. The most likely one to gain electrons is in the top left. The most likely one to lose electrons is in the bottom right. Acid, base, same chart. Yes? That's why they're organized like that. The stronger the oxidizing agent, the weaker the reducing agent is. Yes? The stronger the reducing agent is, the weaker the oxidizing agent is. So, okay, keep that in mind. Next, corrosion. Okay, spontaneous reaction of a metal with oxygen gas and water from its environment. So remember, when you get oxygen and water together, okay, and a metal, it's going to undergo some type of change. Now, if it's iron, example steel, cars, bumpers, things like that, they will rust, because remember, the iron oxide coating is not very durable. It flakes off, right? It basically gets eaten away. It flakes off. Whereas things like, for example, calcium and magnesium and things like that, they form that durable coating kind of thing, right? They have a layer that kind of protects them, and if you chip that away, you get exposed more magnesium underneath it, yes. Okay, but it doesn't flake away as easily, yes? How do you prevent corrosion? Well, painting surfaces, for example, so obviously painting cars, things like that. Painting helps seal in the metal so that there's not direct contact with the oxygen and the water in the air. Electroplating is the process, of course, of electrolytic cells hooking up that metal to the acting as the cathode and plating the metal onto there. Okay, chrome bumpers, for example, yes, is an example of that. Chrome bumpers are basically a layer of chromium over top of steel, right? They're plating on the chromium so that the steel doesn't come into contact with the oxygen or the water. And of course, sacrificial anodes. And when we talk about sacrificial anodes, we talked about things like, well, magnesium's a pretty good one because it's pretty close to the bottom. So, calcium, sodium, magnesium, aluminum, all those things are pretty good at losing electrons. They come before the iron does. So, for example, when you have steel under gasoline tanks, underground gasoline tanks, or if you have a ship, for example, and it's made out of steel, obviously, as the iron hull, you don't want that rusting, so you hook up a sacrificial anode, or you put a chunk of magnesium onto that ship, and that is the first thing that's going to be losing the electrons. It is the sacrificial anode, okay? And then that can just get replaced, and it saves the integrity of the ship or the underground gasoline tanks, okay? Electrolytic cells. Sketch and label a diagram for what a zinc iodide electrolytic cell can be used to produce elemental zinc and iodine. You might see this in two different spots, so two different ways. It's probably, I think I'll do it a little bit backwards this time. I'll probably do the first one this time and then just show you, well, I'll probably just do the first one. But it doesn't have to look like this. It can be anything like that. The key here, though, is two things. It's electrolytic, not electrochemical. Electrochemical basically means electrons are moving. It could be voltaic. It could be, I guess, potentially, it could be electrolytic cell. It just basically means it's talking about electrochemical as just a cell, okay? Whatever that happens to be. This one, it specifically says electrolytic cell, so we know we need a power supply. We know right away that this is not a spontaneous reaction because the power supply has to drive this reaction to take place. So that's the first thing you'll notice. The second thing it says is this: zinc iodide, 2 + 1 - zinc iodide, forms elemental zinc and iodine, like so. Okay, that's the second thing you'll see. So what they're telling you there is that's a really important part of this. All right, we know that zinc, of course, in this ionic compound here, zinc iodide, 2 + 1 - forms zinc and iodine. Okay, elemental. Yes. So we know that's the case. So right away I say, oh, okay, well, how does zinc get from 2 plus to 0? Zinc 2 plus has to gain 2 electrons to become zinc solid. I guess that must be my cathode. Yes? Because it's gaining electrons. My anode, how does I minus basically, yes. Okay, because the 2 is actually just a balance thing there. How does iodide turn into I2 solid? Well, once again, you'd have to balance it, yes. And I'd have to add 2 electrons there, yes. So that, of course, would be my anode. I'm losing electrons. That's important. Okay, it is very important. Because when we get electrolytic cells, people all of a sudden, they get confused because they're like, well, what's going on here? Well, I'm telling you, this is what's going on. Zinc 2 plus wants to make zinc solid. I minus wants to form I2 solid. That's Chem 20 stuff, okay, that you have to kind of review and think about. Why is that important? Well, because then otherwise people start getting confused. How do I know it's zinc 2 plus and zinc solid, and how do I know which one's which? Well, look on your data booklet here, guys. Okay, there's zinc 2 plus. It says zinc 2 plus and 2 electrons. I already wrote this down, I know. Zinc solid, okay, is there. All right, and then you say, okay, well, what about the iodide one? Well, look, it says up here I2 solid, and 2 electrons gives me 2 I minuses. So how do I know what's really happening? I'll tell you how you know how it's really happening. I wrote it out for you already, okay? Zinc iodide makes zinc and iodine, okay? That's how you know. Look, if it's a non-spontaneous reaction, the other part they tell you it's electrolytic. This is lower than this. That's non-spontaneous, correct? That's what I wrote up there. Still acts as the cathode and the anode, but look where the cathode is, look where the anode is. It's non-spontaneous. If we didn't hook up a power supply, this wouldn't work, right? So that's how you know, because here, this is what happens. People think zinc, they hear zinc, so they think zinc, okay, zinc forms a zinc 2 plus. Okay, well, that's here, and that's here too, okay? All right. And then I think I2, iodine, and I minus, they kind of go together, so that's those ones there. So then right away people get confused because they're like, well, should I be using this and this? Or should I be using this and this? Right? How do I know what's actually happening there? And the answer is, well, it's electrolytic. It tells you that. And the second thing is, well, you know, it's that part, right? It's that electrolytic part. Even if they didn't say, you might say, well, you know, well, no, I'm just mumbling now. But anyway, it's in the question. You have to look, okay? You just have to look in the question. What would this look like? Well, chances are, okay, and I did this the other way in first class, and maybe thinking back, maybe I shouldn't have done it maybe quite per se that way. Either way, I'll do both. But this one probably kind of looks like this here. When you're trying to form elemental elements, it kind of has this look to it here. And usually what happens is you basically put 2 electrodes in this solution here, okay? Now, I don't know if it really said, didn't really say, but zinc iodide is my ionic compound, okay? So this is all in a solution here. I'm going to still label this as my anode, and we still label this as my cathode over here. And of course, electrons always flow towards the cathode, no matter what. Okay? However, in this case, you need a power supply to make that happen. All right? So I'm going to need a power supply to force the electrons there. Don't forget, in that power supply, right, you have to think about what's happening here as far as negatives and positives as well, right? They are basically forcing the electrons to this side here, so positive, and then they are pushing them this way. So negative would be here, and a positive of that basically would be there, right? So it is basically pulling the electrons on that power supply, the positive end would be there, pulling the electrons towards it, and then they're pushing them towards the cathode, okay? we already talked about what's where, because that's the beauty about doing the first part. I know that over here, anode, that's where I'm going to be losing electrons. That's the iodide part. And the zinc, of course, is going to be gaining electrons there. Probably what you have here is a solution of zinc iodide, I imagine. Okay, like so. And what happens is, of course, remember, this really is the zinc 2 positive and the I minus, yes? The zinc 2 positive is going to basically be drawn towards the zinc. You would have a zinc here, cathode, okay? Because the zinc cathode, like that, okay? So the zinc 2 positive is probably going to want to attract to here because the electrons are coming over there, and it's going to get plated onto there, okay? And you can pull that zinc out, that zinc electrode out after a while, and there'll be more zinc on there. The I minus part is going to be attracted to over here. However, I minus forms iodine solid. Is that electrode here? This is electrode, right? Is that iodine here? Why? It's crystals and it's not a metal, correct? So we need to have metals there, yes? So it's attracted to over here. That's where it's going to take place. I minus is going to turn into I2 solid. It's not actually going to happen on the electrode, okay? Or if it actually does, it'd be at the bottom here and probably just fall off anyway. Here, you're going to need a inert electrode again, like a carbon or a graphite or platinum or inert, okay? And that's what's going to happen there. So basically, the zinc ions are going to turn into zinc over here at the cathode, and the I minus ions are going to turn into I2 solid over there, okay? So it could look like that. It could also have two separate half reactions as well, where in one you got I minus turning into I solid, and the zinc turning into zinc 2 plus, or zinc 2 plus turning into zinc solid. Yeah.
Does it matter which one's like higher up on the chart?
It's a matter of with electrolytic cells. I'll tell you this: with electrolytic cells, it's really going to come down to this stuff here, because that's going to tell you basically the things that you should be looking for. Well, it says zinc iodide wants to turn into zinc and iodine. So how does zinc 2 plus turn into zinc? So that's what you want to look for, okay? That's really, really important for electrolytic cells. If it was a voltaic cell, then not as important, because it would just have, it would just say, you know, it's a little less specific with voltaic, because they'll just tell you that it's like, it's a zinc half cell and an iodine half cell, for example. And you just look up, find which one do you run into first, which one do you run into first, make the reaction between those two, and that's the cathode and the anode. Higher up it is. Top left, work your way down. Bottom right, work your way up, right? Cathode always. Yeah. Okay. All right. Applications of electrolytic cells. We kind of talked about this a little bit. Production of elements, of course, so you can make cations, and cations turn into metals, anions turn into nonmetals. Refining of metals, so you could do copper refining things, for example. We gave you notes on this. There was a package of, it was just notes that day on applications of electrolytics. It's called applications of electrolytic cells. Refining of metals, electroplating, so chromium onto bumpers, things like that, right? And finally, recharging batteries, reversing the flow of electrons to recharge up that stuff, okay? Very last one here, good old-fashioned stoichiometry, a little bit more. What do we got to do with this one here? Well, first thing I see that's kind of a standout for me, I guess, is this right here. Current, 7.50 amps. 30 minutes. What formula is that? Faraday's law, yes. Amount of electrons, IT over F, yes. So, before you can do that, it says we're going to talk about scandium ions. And this doesn't really matter too much, but listen, you should still be able to figure this out. Because sometimes they like to do scandium ions and zinc ions, for example, or zinc solid, or whatever the case might be. So you should still be able to figure this out. This is a pretty simple one of this here. It says what mass of scandium will be produced. So what mass of scandium is produced? If I had to write out an equation for that, I'd probably say something like this here. Scandium, by the way, forms a 3+ charge. You can look that up in your data book or in your periodic table. What mass of scandium will be produced? Okay, so that's how I know I probably should write it out like a reduction half reaction. Okay, that's the only way. If you wrote it backwards, would you get the same answer? Yeah. Okay. However, like I said, if we add something else into there, you want to be careful which way you're going with that stuff. All right. So what I need to figure out is N here. Because if I can figure out the amount of electrons here, I would know the amount here with, of course, the molar mass. How am I going to figure out how many electrons do I have? Because I know the molar mass of scandium. I could tell you that right now. I have it written down here somewhere. It is 44.96. So I know that. Right? And I think you guys know how chemistry works. If I'm looking for a little m there, I need to know n. Where am I going to get n from? Well, probably over there, yeah? So I need to, of course, look at my formula here. Amount of electrons equals IT over F. And that, of course, this is amount of electrons, amount, N, yes? Has to be measured in amps. This has to be measured in seconds. And this, of course, is in coulombs per mole, which is just the number 9.65 times 10 to the 4. Okay? Which, of course, that one is in your data booklet, 9.65, because it's a constant, so that's in there. Amount of electrons. I have, what, 7.50 amps, I think? Let me just double check. Yeah, 7.50. I have 30 minutes. 30 minutes, I got to change that to seconds, so that is 1,800 seconds. All over 9.65 times 10 to the 4 coulombs per mole. Amount of electrons is, therefore, about 0.13989 moles. So that's the amount of electrons that are being transferred in that amount of time at that voltage. That's the amount of electrons being transferred or basically being moved. Well, if that was 0.13989 moles, then I know divide by 3, okay, to get over to there, divide by 3, then this should be about 0.046 moles here. And roughly, and then multiplying those two together, I will get 2.1 grams final answer there. Yeah. Well, it's a 3 to 1. 3 to 1 ratio. Okay? And that is a little bit of Faraday's law there to finish it up. Yes? Good?